Hello everyone, welcome again to Discrete Mathematics and its applications. Now, we finished the discussion on operations on binary relation on this theorem. So this theorem gives us a connection between the concept of transitivity and the powers of binary relation. The theorem states that a binary relation R over a set A is transitive if and only if R to the power of n is actually contained by R for every n from 1, 2, 3, 4, and so on. So this is a statement that is very useful because that means to show that a relation is transitive, we could do that by showing that R to the power of n is contained by R for every n from 1 to 2, 3, 1, 2, 3, and so on. So let's prove this theorem. The proof consists of two parts because we have if and only if statement here. The first part is the if part and the second part is the only if part. So let's start with the if part. The if part says that R is transitive if or let me just write it more clearly. We show that if that R is transitive if R to the power of n is contained in R. Yeah, for every n from 1, 2, 3, and so on. Now, how do we show that? Well, suppose we start with the premise, right? The premise is this. Yeah. Suppose R to the power of n is contained by R for all n from 1, 2, 3, and so on. Then obviously R to the power of 2 is contained by R, right? Because this holds for n equals to 2, right? And this is the same as this is equivalent to saying that R composed with R is contained by R. Yeah, this implies that whenever you have a pair A comma B in R, uh, oh no, let's write it this way. So suppose you have this implies that A comma C is in R, composed with R. So the composition of R and R, if and only if there is a B in A such that um, A comma B in R is in R and B comma C is in R. Yeah. Now, yeah. What? So does this mean that R is transitive? So is R transitive? Well, the answer is well, so suppose you have a pair A comma B in R and B comma C in R. by this statement, by the previous statement, we know that A comma C must be in R, circle R, right? But because R circle R is a subset of R, or is contained by R, therefore A comma C must be in R. So R is transitive. This is what we want, right? So from the assumption that R to the power of n contained by R, we get that R is actually transitive. So how about the opposite direction? Yeah, we show that if R is transitive, so the opposite direction, the only if part, right? Then R to the power of n is contained by R for n from 1, 2, 3, and so on. So to show this statement, we use mathematical induction. We show this using mathematical induction, right? Because we want to show this holds for n from 1, 2, 3, and so on. So the base case is when n is equal to 1, right? This is trivial, right? Which is trivial, yeah, since we know that well, R to the power of 1 is actually R by definition, and this has to be trivially contained by R itself, right? So it holds. Now assume for induction that if R is transitive, then R power of n is contained by R. So for induction, we show that if R is transitive, then R to the power of n plus 1 is contained by R. Now we have that actually we have that or let's start with the premise. So suppose R is transitive, right? So then what do we get? Then R to the power of n plus 1 is actually R to the power of n composed the composition of R to the power of n and R. Now by the induction hypothesis, we know that because R is transitive, we know that R to the power of n is contained by R, right? So therefore R to the power of n composed or circle R to the power of n circle R cannot be bigger than R, right? Yeah, so that is by this we know that that this must be contained by R, circle R, which is R2 and sorry, which is also contained in R since R is transitive. So uh, so we established the statement for R to the power of n plus 1. So therefore the induction is complete and the statement holds, right? So you have the proof of theorem 5 giving this if and only if relation between transitivity and the powers of binary relation. And with this we stop here, and we shall continue in the next video series on closure operation.